It's my great pleasure to welcome everybody here for the school for this super important topic. Clearly, ocean and its coastal areas have a significant impact on Florida. In particular, the economy of Florida is extremely dependent on the health of our ocean and coastal areas. So we are truly delighted to welcome everybody to listen a little bit about what's happening in that front. And I want to take this opportunity to thank Provost LeBlanc, who is representing the University of Miami today, as well as two members of our boards of visitors, Cheryl Gold and Sandy Batchelor, that are here with us as well to listen more about this topic. We have also from the Rosenstiel School, Professor Lisa Bill, our Associate Dean for Research, that is taking this issue super importantly as well. Okay, we need to be able to provide leadership in this area. The Rosenstiel School in general is doing cutting-edge research in the process of educating the next generation of scientists. Okay, this is really a super important mission for us. And then we create knowledge that we transfer and we pass to our undergrad program and the community in general. And within that framework, this is why we are so interested to provide this meeting today. We have with us other people also from the NOAA AOML, the Atmospheric and Oceanic Meteorological Lab, and from CIMAS, which is cooperative institutions that exist between the NOAA and the different organizations. So CIMAS is one of those establishments here at the school. We have representatives from Ocean Conservancy, and we are truly delighted to lead this activity today with them. We have people from the Florida Keys National Marine Sanctuary, from Oceana, Monroe, Miami-Dade, Broward, and Martin counties, and many others that have been able to join us. We just completed at Rosenstiel a strategic plan for the next few years. We hope that it's going to be in effect for the next 5-10 years when the university is transitioning to its second century. And as part of this strategic plan, we are putting an emphasis, obviously, given the activities that we do at these schools, on some of the activities that are going to be discussed today. So without further delay, it's my great pleasure to introduce Professor Thomas LeBlanc, the Provost of the University. Thank you.
Thank you, Dean Avasar, and thank you all for joining us here today at the Rosenstiel School. On behalf of President Julio Frank and the faculty and staff of the University of Miami, we'd like to welcome you all to this very important topic, this workshop on ocean acidification. I'd particularly like to welcome and thank Congresswoman Ileana Ros-Lehtinen, who will be joining us later today, and her legislative assistant, Wesley Brooks, for being here. State Representative Holly Rothschein, and Honorary Consul General of the Principality of Monaco in Miami, Thomas Abreu. And also we have a representative from Congressman Carlos Curbelo with us. And I'd like to thank them all for taking the time to learn about this critical topic. This is not a topic about politics, this is a topic about science. And it's really important that all of our leaders understand the science of ocean acidification. As a university committed to excellence and relevance, we recognize our responsibility to convene the thought leaders in search of answers to our community's most pressing problems. We are honored to collaborate with the Ocean Conservancy to bring the ocean acidification conversation to Miami, which is ground zero for several climate change-related issues. This collaboration aligns the university's commitment to serve as a hub that connects people, ideas, and solutions, both in our region and around the world. As Ronnie mentioned, the University of Miami will celebrate its centennial just 9 years from today, which means this institution has been an integral part of the academic, cultural, and economic development of South Florida for the past 91 years. Now more than ever, we are acutely aware of our community's environmental fragility as well as the potential for environmental problems to jeopardize everything we have built together. In just the last few months, I've spent time in Antarctica, where you can see climate change up close, and you can see the vulnerability of fish populations, penguin populations, to what man is doing. I just arrived here today from England, and I spent time with a number of folks who are trying to eat totally organic. This is a country whose entire history has been built on the back of the oceans. And as the oceans change out from and under them, what will it mean for island countries, for coastal cities, for our food, for our fish populations, and for the human race? Ocean acidification, sea level rise, and climate change are highly complex, multidimensional problems that can be understood only by applying many different lenses to generate a more complete picture. As a dynamic research institution, the University of Miami has mobilized expertise throughout our 11 schools and colleges and our numerous interdisciplinary centers and institutes towards the urgent goal of designing a sustainable future. The university recently published an online comprehensive climate change special report, which you can find on our homepage, that details the extensive work here at the Rosenstiel School and throughout the university in engineering, in architecture, in public health, and many other fields. This report is more than informative. It serves as a platform for our faculty, students, and researchers, both within and outside the University of Miami community, to network and discover opportunities for complementary collaborations. One such collaboration is today's program, a joint effort of the Rosenstiel School and the Ocean Conservancy to shed light on ocean acidification. We look forward to this being the first of many discussions that unite scientists, stakeholders, and policymakers to broaden our understanding of global problems, exchange ideas, and enhance our research activities. Thank you all for being here, and I hope you enjoy the day.
And now it's my pleasure also to introduce to you Jeff Waters from the Ocean Conservancy, and he is the Director of Government Relations at Ocean Conservancy. Jeff.
Thank you all for being here. I'm Jeff Waters, and I'd like to welcome you to this event. Thank you so much to the Provost for your comments and remarks. So at Ocean Conservancy, we've been working on ocean acidification since about 2011, and our program is focused on basically two main areas. The first area is the science of ocean acidification, and that's the first area that we're going to come together to discuss here today with our first panel. The science of ocean acidification is evolved enough that we know enough to know that we should be very, very nervous. But what we don't know is astounding. There are enormous amounts of volumes of questions that need to be asked and answered, and we need academic institutions like the University of Miami to help answer those questions, to help bring light to the dark where we currently don't know what we're facing or what might potentially be around the corner. The second area where we have a major focus is on people. Because ocean acidification, while we delve into the science and the research and all of the questions that we don't know, at the core, it is an environmental issue that is going to impact and is impacting people. It's not just an academic problem or a theoretical problem. It's something that is here and now. And in certain parts of the country, for example, in the Pacific Northwest, it has brought industries to its knees already. That might potentially happen here. It might potentially happen anywhere in the country. We're not totally sure, hence coming back to the science. So our two panels that we're bringing together today are focused on those two areas of inquiry, first being the science and second being the people and the stakeholders. So if our first panel can start to make their way up here, I'll give them a very brief introduction. So leading that panel, and I'll let Terry kind of take the lead in terms of introducing the panel itself. But Terry Gibson is a fourth-generation Floridian who grew up in West Palm Beach, a lifelong and very avid, extremely passionate recreational fisherman, as well as a writer and advocate. We've had the pleasure of working with Terry for many years, and deeply appreciate all of the work that he does. So he's going to talk through a lot of the science and what we know with our science panel. So if they can make their way up here, we can start to delve into this conversation. So I think Terry's going to basically lead us off and start the discussion, but we certainly intend this to become a conversation with the entire room, with questions and answers as we delve into these questions together to try to figure out what we're facing in this arena. So Terry, thank you.
Good morning. Thank you, Jeff. My name is Terry Gibson. I'm the owner of Northwell Media Consulting, and I spent most of my career in essence, a science communicator, and it's extremely significant that we're having this conversation about ocean acidification here at Rasmus today. I have been through the likes of Jerry Alt and many other scientists here. I've always had access to some of the best experts in the world dealing with some of the biggest problems we have in fisheries management. They've always been so accessible and so clear in helping me and translate things downward to the general public about what faces us in fisheries and in our general environment. I just want to thank everyone associated with the university personally for really helping my career to advance and for advancing the general knowledge of marine science. To that end, let me introduce our panelists today. We have Kim Yates is an oceanographer with the U.S. Geological Survey. Her expertise is in basically the way things are dissolving, it sounds like to me, from the one conversation we've had on the phone. But I will let her talk more about her research. Chris Langdon, I've had in the middle here, I've had the pleasure of seeing present a number of times. He deserves an outstanding community service award for all the time he spends, I suspect for free, trying to educate people about climate change and what it's doing to us here. What it's doing to guys like Ray Rocher I saw earlier and me who make part of our livings on the water, in my case part, in Ray's case all of. So Chris, thank you for everything that you've been doing, and we look forward to hearing your thoughts again. And last, we have Ryan Woosley, who's an assistant scientist here at Rosenstiel, and Ryan is a chemist, from what I understand, and I'm going to be very blunt. I begged my way through science and chemistry through high school and college. So if I stand up here with a dumb look on my face, it's because I don't understand. So anyway, I guess we should proceed with the presentations. And in what order did we decide that we would proceed? With Ryan first, correct? That's right.
So I'm Ryan. I study the chemistry of ocean acidification. So I wanted to discuss what is ocean acidification and why is it happening. As I'm sure everyone's aware, burning fossil fuels for energy produces carbon dioxide, which we release into the atmosphere. But only about half of that actually stays in the atmosphere. The other half gets split between being stored in the land on plants and dissolving in the ocean. And that fraction that dissolves in the ocean is what we're concerned about today. The reason it dissolves in the ocean is pretty simple. The atmosphere and the ocean like to be in equilibrium. So the concentration of carbon dioxide in the atmosphere is about the same as that in the ocean. So what happens if we increase the amount of carbon dioxide in the atmosphere? It shifts that balance, and there's now a drive for that CO2 to go into the ocean. And that will continue to occur until the concentrations are equal again. And where does this occur? It occurs everywhere. All the surface oceans have been shown to take up this carbon dioxide. But as you can see from this figure, there's a hot spot in the North Atlantic. The majority tends to go into the North Atlantic, and this is a result of ocean circulation, and that includes the area off of Florida here. What we're really concerned about is what happens to the CO2 once it gets into the ocean. And the reason is it reacts with water to form a variety of different products. The majority are bicarbonate ion with a little bit of carbonate ion and just trace amounts of bicarbonate or carbonic acid. So if we increase the amount of CO2 by dissolving it in seawater, it shifts these reactions towards the bicarbonate ion. And that also produces a hydrogen ion. So the net result is an increase in carbon dioxide, bicarbonate, and hydrogen ions, and a decrease in the carbonate ion. And we measure this through pH, which is the concentration of the hydrogen ion, and a measure of the acidity, which is why we call it ocean acidification. Seawater has a pH about 8.05, which is slightly alkaline, and lower number means more acidic. This is a log scale, and that means what looked like very small changes can actually be very large. Since pre-industrial times, the acidity has already increased by about 30%, and if we were to burn all the fossil fuels available, it would increase by over 500%. And we know this is happening because we can actually measure it. One way we measure it is through an international program that measures the chemistry of the ocean through repeat lines every 10 years, looking at the changes in the chemistry between those 10 years. And this shows a recent cruise that in the Atlantic from Iceland all the way down to Antarctica that measured the decrease in pH of about 0.02 in the surface ocean. And in 10 years, that's an increase in acidity of about 5%. And there's indications that that rate is actually increasing. What were to happen if we burned all the fossil fuels? The pH would get down to around 7.4. And once we stop, whenever it stops, it's going to take a long time for values to come back to what they were before, at least several thousand years, if not longer. And the reason this is important to Florida is that carbonate ion. The carbonate ion is used by organisms such as corals and other calcifiers to make calcium carbonate skeletons and shells. If we decrease the carbonate ion, that decreases their ability to make these shells and their ability to grow. And that's what Chris and Kim will discuss.
All right, so I'm going to be talking today about the effects of ocean acidification on Florida's coral reefs. And we used to think that this was a problem for the future, that it wasn't an immediate threat, that we may have had another 50 or 60 years before things got very critical. But I'm going to show you some surprising results from some recent research I did to show that some parts of the reefs in Florida are already in trouble and, in fact, dissolving. So I like to start my talks about ocean acidification by reminding people about what the CO2 concentration in our atmospheres looked like over recent history. So this is going back 1,000 years. And you can see that up until the year 1800, it was quite stable. And in fact, it was at that level, we know, going back 800,000 years. And then starting in 1800, which is when the Industrial Revolution started, and when society started switching over to burning fossil fuels, we can see the rapid increase of CO2 in our atmosphere ever since. So one of the proofs that humans are causing this problem is this coincidental timing. CO2 used to be very constant in the atmosphere, and since we started burning fossil fuels, it's been increasing exponentially. Another interesting line of proof is that fossil fuels, carbon, contain none of the radioactive isotope carbon-14. It's all decayed away. So the fossil fuel CO2 has a chemical fingerprint, and we can match up how the CO2 in our atmosphere has increased since 1981 with the changes in that chemical fingerprint in the CO2 in our atmosphere, and you can see that they match up beautifully. So that's, I think, the firmest incontrovertible proof that humans are causing this CO2 to increase and cause this problem. If it was volcanic CO2 or some other natural source of CO2, we wouldn't have this changes in the isotopic composition of the CO2 in the atmosphere. So this figure shows how CO2 is projected, or the pH of seawater is projected to change in response to those changes in our atmosphere. As Ryan mentioned, about 30% of all the CO2 that we release into the atmosphere each year dissolves into the ocean. It's already reduced the pH from 8.2 to 8.08 or so. That's about a 30% increase in acidity. And by the end of the century, it could be down as low as 7.75, and that's a doubling in the acidity of the ocean. So this lower line is what we call the business as usual scenario. So it's assuming that human population's increased and everyone's using fossil fuels at the same intensity that they are today. And then this other curve up here, very low CO2 emissions, was a very, very optimistic one that we would have already drastically started to cut our emissions back in around 2010. So we'll fall somewhere between those two extremes, but right now we're headed along the path of that lower curve. So as the pH of the ocean declines, which is the lower axis on this graph, what changes along with it is something called the saturation state. And that's related to the carbonate ion concentration that Ryan's talking about. And that's what the organisms in the water actually care about. And you can see that there's a nonlinear relationship between pH and saturation state. So biologists prefer to talk about things in terms of the saturation state because there's a linear relationship between that and its effect on organisms. So you can see that the pH is around 8.05 today, and as the pH declines, at some point by the end of the century, we're going to be reaching points where the ocean could become undersaturated. So what I'm really talking about today is the research that I conducted with NSF funding in 2009 and 10 to get the state of the coral reefs in Florida. So we took the university's ship, and every 4 months we left Miami and went south and did these onshore, offshore lines of between 3 and 5 stations along an onshore, offshore axis along the reef track. And then we collected water at what's indicated as the ocean station. And then in the Middle Keys, and I'll talk about this later, NOAA has an ocean acidification buoy located on the southern tip of the island of Murata, where it's continuously monitoring the pH of the water since December of 2011. And I'll show you some of that data in a while. All right, so the results of the cruise were to measure the calcification rates of the reefs, their ability to build their skeletons. So we have the lower keys on the left, middle keys in the center, and the reef tracks representing the upper keys on the right. And we observed a strong seasonality. During the spring and summer, the reefs are actively building their skeletons, and that's indicated by the blue bars. And that's what we expected to see. But surprisingly, during the fall and winter cruises, we saw that in the middle keys and upper keys, that the reefs were actually dissolving. In the middle keys, just a little bit, but at Fowey, the northernmost reef, they're dissolving a lot during the winter months. If we convert this data to the annual rate, so we just add the seasons together to get what the total annual production is, you can see that in the middle, or in the lower and middle keys, the reefs are still building their skeletons at a slow rate, but at a rate. And as we get into the upper keys, at Penny Camp, they're just barely hanging on. The annual average was just 0. And at Fowey, the northernmost line, on an annual basis, because the winter rates were so much in excess of the summer production rates, they're actually wasting away today. So why is this, and how is this related to ocean acidification? This is a pH record from that buoy that I showed you off the southern end of Isle of Murata. So it's been recording the pH of the water every 3 hours since December of 2011. I haven't put the years in, I'm just stressing the seasons here. I've highlighted that you can see that there's a normal periodicity or cyclicity in pH, and it goes through a minimum each fall and winter. So between September and mid to late December of each year, the pH is going through a minimum. And this is partly due to temperature, but much more strongly due to the productivity and, in fact, the breakdown of the plants, respiration during the winter months. So this pH by itself is not low enough to cause anything to dissolve on the reef. What really matters, the dissolution is actually occurring in the sediments and in the framework of the reef. And the pH of that water starts at whatever the overlying water is, but then the metabolism of the organisms living in the sediments, the bacteria and the other invertebrates, respire. and they're releasing CO2 into the water, or into the pore waters, decreasing the pH. And they can do that until they run out of oxygen. And that's sufficient to lower the saturation state in the pore waters to the point that it will actually start to dissolve. So this blue line is what the saturation state of the pore waters would have looked like during the middle of the early parts of the Industrial Revolution. This next line is where we are today. So you can, and this is the actual measured data from that buoy. So you can see that during the fall, for a period of about a month each year, the saturation state in those waters is getting low enough to cause it to dissolve today. And this is in the Middle Keys. We don't have data for the Upper Keys, but it would be even more exaggerated. So now we can, making some assumptions, look at what would happen going into the future based on projections of how that pH will decline if the CO2 emissions continue to increase in the atmosphere. So that's 2020, 2040. So you can see that now, as we move decades into the future, more and more of the year we're going to be in this phase where the corals can dissolve. All right, and if I take this all the way out to the year 2100, we're on that lowest black curve. So completely below that heavy white line, which is the point where calcium carbonate will dissolve. So somewhere between 2080 and 2100, I would predict we're going to be in this very critical stage where the reefs could be dissolving year-round. So what explains why we're seeing this more in the Upper Keys than in the Middle and Lower Keys? So on the left panel, I'm showing you the calcification rate data. This is the same data I showed you before, except I've lumped them into Lower, Middle, and Upper Key stations to improve the statistics. And then on the right, we also measured the production and destruction of organic matter at those very same stations. And look at how parallel and the symmetry between these two data sets. So what I think what's happening is the metabolism is driving the dissolution that we see on the left. So if we plot calcification rates on the y-axis against those production rates on the x-axis, we see this really striking linear relationship between the two. And so here's the Upper Keys during the winter and the Middle Keys during the winter. And if we're below this line, that means we're dissolving. And if we're to the left of this line, it means we're net respiration. So the amount of dissolution that we're seeing in the Upper Keys is explained by the fact that the respiration rates there during the winter are greater than they are in the Middle Keys during the winter. And then in the Lower Keys, we're not seeing low respiration rates, and we don't see dissolution either. So what I think what's happening is respiration is driven by the breakdown of organic matter. And that's produced, nutrients need to be available for that. So I think we may be seeing a nutrient signal, a nutrient eutrophication signal up near the Miami area that's driving these high rates of respiration, which are driving the pH in the pore waters down to the point that they're dissolving more there than in other parts of the Keys. So that's chemical data that might be kind of esoteric to a lot of people. These are actual photographs of reefs, reefscapes we like to call them. And this is from Carysfort. So this is a coral reef located in the Upper Keys, so this area of concern. And you can see these two top pictures are taken in 1975 and 76. This area, back in those days, had extensive stands of the elkhorn coral and the staghorn coral. And then in the 80s, a disease came out through the entire Caribbean and pretty much killed these two species. So that in 2004, both these species are dead. But you'll notice that the skeleton, the physical structure, is still there. But and then this is a picture I took a few months ago in 2016, and this same area today is a flat expanse These pieces you see here are the dead skeletons of the staghorn coral above. But all that three-dimensional structure, which is what the fish need to live, has disappeared over that period of time, or maybe longer. We can't really pin down the time period. But so this is what we're talking about, a really dramatic change in the reef structure in the Upper Keys. And this is going to have impacts on the fish that obviously that these reefs can support. Now, and I want to finish this by mentioning this isn't the only thing that's going on, obviously. There's also the bleaching. So there's this record here showing in gray temperature record, heat stress records going back to 1987. And then since 2005, the amount of corals that are observed to be bleached in each of these years. So you'll recall that 2014 and 15 were the two warmest years on record, and very high percentages of corals bleached over those 2 years, between 30 and 40%. So I want to stress that as we study ocean acidification, we're not studying it by its lonesome. We're studying it in the complete context of all the other stressors that are going on as well. So just to wrap up and to talk about what we should be doing, losing the reef structure is a game changer. I mean, ocean acidification can affect the behavior of animals, affect reproduction rates, and we need to study those. But if the reef itself, the structure disappears, nothing else we do is ultimately going to matter. I'm not saying we shouldn't do it, but we need to be addressing, the only way to reduce, prevent that happening is reducing our CO2 emissions. In the meantime, we can do a number of things to keep the corals alive, essentially first aid to restore them and keep them going, find strains that are more tolerant than others are absolutely important things to be doing. But we really got to get serious pretty soon about reducing our CO2 emissions.
Good morning, everyone, and I wanted to thank everyone for being here, and I want to give a special thanks to University of Miami and the Nature Conservancy for organizing and hosting this event for us today. So I am with the U.S. Geological Survey, and many of you might not know, but the U.S. Geological Survey is one of our only non-regulatory federal science agencies. And I actually work within the Coastal and Marine Geology program. And we actually do more than just geology. We're what we call a multidisciplinary agency. So we have scientists from lots of different disciplines working together, and we like to address problems from the regional scale and across those science disciplines so that we can begin to understand how issues like ocean acidification affect whole ecosystems. And so I am actually a biogeochemist. It means I know a little bit about a few things and not a whole lot about anything. But I work across all the disciplines and try to approach these problems from that whole system, multidisciplinary aspect. We like to understand the regional context of the issues that we're working on, and particularly emerging concerns related to that regional context. And Florida is rather unique in that both within the region and within our nation, it's one of the only states that's actually built on what we call a carbonate platform. So I want to spend a little bit of time developing that regional context for you so you can understand some of the broader implications, and really I'm going to generate more questions and answers for you today. But Florida's carbonate platform, this is a picture of the state of Florida and that carbonate platform, was developed about 5 million years ago when shallow tropical sea covered most of the Florida peninsula. Carbonate-producing organisms like corals and shellfish produced thick accretions of carbonate that form that platform that extends all the way out to the edge of the continental shelf. And then over time, changes in sea level submerged and exposed the carbonate platform, creating what we call karst. This is actually a picture of what that karst topography looks like. And essentially, what we have in Florida is we have a very thin layer of sediment that overlies our bedrock. And you can see a lot of solution holes. It kind of looks like Swiss cheese. And that's what we call karst topography. And most of our bedrock within Florida has this kind of topography associated with it. So this karst actually forms our sinkholes in Florida and our aquifers through a process that looks very similar to ocean acidification. Ryan talked a little bit earlier about how carbon dioxide can combine with water, and this actually happens in the atmosphere. and that can create carbonic acid, which falls out onto the surface in rain. That percolates through this thin sediment layer on the surface that we also call a mantle, and it eventually starts dissolving the carbonate bedrock underneath. And it eventually dissolves enough of it that that carbonate bedrock begins to collapse and form sinkhole features. This karst also forms our aquifer system, and this is a cross-section of what our Florida aquifer system looks like. And that aquifer system holds most of our groundwater and our drinking water in Florida, and it also creates what we call leaky coastal margins. So it provides conduits for groundwater to flow from the land to the sea. And this is really what connects our whole ecosystem in Florida. It's what connects the terrestrial ecosystem with the coastal and marine ecosystem. And so you can begin to see how water movement in Florida becomes very important and why we're so concerned about things like ocean acidification. Also, our coastlines and our coral reefs are supported by this carbonate platform. This is actually a cross-section of what the carbonate platform looks like in the Florida Keys. And in many areas along the coastline of the Florida Keys, my arrow here, you can see the bedrock is exposed. And it's this carbonate platform and that bedrock that actually protects our coastlines from erosion and protects our real estate from erosion. Our coral reefs also grow on top of this carbonate platform, and these coral reefs actually form natural barriers that help protect us from coastal hazards like storm waves and also erosion. So we're particularly concerned because we've been seeing coral reefs degrading for some time over the past few decades. We know that ocean acidification is impacting Florida's coast. We know this because of research like Chris's that shows that it's already beginning to occur. And I want to take just a minute to talk about the difference between coastal ocean acidification that's non-climate driven and also ocean acidification that is climate driven. And one of the things that we see is we do have ocean acidification that are caused by local factors like eutrophication, which Chris talked about a little bit earlier, and also things by like upwelling of deep ocean water that has a higher CO2 concentration in it. And also flow of fresh water like groundwater and surface water flow causes ocean acidification as well. And so these things happen at the local extent. And then also we have ocean acidification caused from increasing atmospheric CO2. And that can exacerbate those coastal ocean acidification processes. And that's what Chris was showing earlier today. Other reasons we know why ocean acidification is occurring, within the USGS, we've actually been synthesizing historical data from some of our local and state water quality monitoring programs. So for example, one of our scientists, Lisa Robbins, has been synthesizing data from the Department of Agriculture and Consumer Services, and this shows that pH around the coastline of Florida has been decreasing since about the 1980s. We also have a student intern who just finished a project looking at Southwest Florida Water Management District pH data from back to the 1990s in some of our major spring groups. And that data shows that our springs are also decreasing in pH since about the 1990s. And we know that coral reefs are also beginning to degrade. And so these are the kinds of observations and the kind of evidence that let us know that ocean acidification is happening now in Florida. This is not just an emerging concern that we didn't expect to see for another 40 or 50 years. This problem is here today, and we don't have time to not deal with it. We can't wait 40 or 50 years to begin thinking about it. One of our biggest concerns in the USGS and where we're focusing much of our work right now is how ocean acidification might affect our vulnerability to coastal hazards. So for example, we know that these coral reefs have been degrading due to a variety of local factors for the past few decades. And Chris showed us that our coral reefs are already beginning to dissolve in Florida during certain times of the year. So we know that these erosional processes are taking place, but what we don't know is the full extent of how much erosion has already occurred and how much seafloor that we've already lost, especially given that this degradation has been taking place for the past few decades. So one of the things that we're working on right now is we're doing a regional scale analysis to measure that erosion throughout the Florida Keys. And the way that we're doing this is we're actually looking at historical hydrographic data from NOAA combined with modern day bathymetry or water depth data that we collect at the USGS to actually measure changes in seafloor elevation. And so that tells us how much erosion has occurred, not just from ocean acidification, but from all of the other impacts to our Florida reefs as well. But by doing that, that allows us to begin to tease out how much change is caused by ocean acidification as opposed to some of these other factors. And then we can combine that with certain process studies. And what that allows us to do is to not only measure how much change has taken place in the past, for example, in this particular study from the 1930s to the 2000s, but also to predict how much more change is going to take place in the future, and then use that to determine how things like wave heights might increase and how erosion might increase in the state of Florida. And so that's some ongoing work that we have right now, and we expect those results to come out sometime in the fall. We're also concerned because ocean acidification affects the habitats that support our fisheries. There was a recent study that came out in Nature Climate Change. It was a risk analysis of the southeast region to ocean acidification. And it showed that Florida estuaries are at particularly high risk of low saturation waters. Remember, we talked about saturation state a little bit earlier. And this is specifically due to eutrophication. And so our estuaries are beginning to become more vulnerable to climate-driven ocean acidification as well, because they're particularly vulnerable even to the local processes. That study also showed that Florida actually has a low adaptive capacity with respect to ocean acidification, and this is because relative to the other regions in the United States, we actually have a relatively low diversity of commercially harvested shellfish that we have here in Florida. So these are other issues that concern us. And it's not just loss of habitat structure, but it's also impact to specifically our shell fisheries industry and how ocean acidification might prevent them from growing properly as well. So really, I'm generating more questions than I have answers. A lot of these issues are emerging concerns. We have a lot of people working on these things. We know that ocean acidification is happening. We know how it affects certain species and things like carbonate dissolution. However, we don't know what those longer-term impacts really are going to be. So the big questions that we have are, how will ocean acidification affect and be affected by the carbonate structure of Florida? Are there going to be any impacts to our aquifers and drinking water supplies? We really just don't know. How will chemical erosion affect sinkhole formation, our coastlines, coral reefs, and specifically coastal hazards associated with coral reefs, once those natural barriers are degraded to the point where they're not helpful anymore? And then ultimately, how might these structural and chemical changes impact the organisms that live on that structure? How might it impact the biology and ecology of Florida's both the terrestrial and marine ecosystems? So at this point, people always begin to wonder, well, heck, is there any hope at all? And actually, there is some hope. There are actually what we call winners in ocean acidification. So for example, things like seagrasses and certain species of marine algae actually benefit from ocean acidification because it increases their growth rates. So for example, seagrasses grow through photosynthesis. We all learned that in grade school what photosynthesis is. That's much like terrestrial plants grow. And that process actually consumes carbon dioxide, it produces oxygen, and it can actually increase pH. And so in fact, things like seagrass beds and some algal beds might actually be able to locally increase pH and buffer ocean acidification and help those organisms that are negatively impacted. And in fact, most estuaries, while they show a decrease in pH, we do have some cases where we see increasing pH in estuaries. So for example, in Tampa Bay, they lost a lot of seagrass, and in the early 1980s, they put together a nitrogen management plan to reduce the nitrogen loads to Tampa Bay. And as a result of that, they've been able to recover and regrow seagrass since that time. And we've seen a direct correlation between the increase in acreage of seagrass in Tampa Bay and an increase in pH. And so one of the things that we're working on is studying how areas like that actually might serve as natural refuges for marine organisms from ocean acidification. One of the other really interesting discoveries that we've made is we're finding that certain mangrove communities can actually protect reef-building corals from ocean acidification. And this is really interesting because corals in general don't like to grow in mangroves. They're just not usually the right kind of habitats for them to grow in. This is an example of a picture from St. John in the U.S. Virgin Islands. And we found 33 species of reef-building corals actually growing underneath and attached to mangrove prop roots there. And we've studied this ecosystem for the past few years, and we've been able to show that these corals are actually getting protection not only from ocean acidification, but from ocean warming as well. The picture next to it is a picture just outside of these mangroves, and corals are just struggling to survive there. And this is actually a very unique place in the world. You won't see a place like this with this much diversity, but it is one possible type of refuge, natural refuge, that can protect these corals. And in fact, we are seeing some cases in Florida where these kinds of natural refuges are popping up. In a recent study, we found that seagrass beds in the middle Florida Keys are in fact actually locally elevating pH and can provide protection from ocean acidification for things like corals and shellfish that grow there. And those are what we call natural ocean acidification refuges. And as a matter of fact, we do now have some observations of corals beginning to grow in the mangroves along the coastlines in the Florida Keys. These right now are observations that are being made by the Fish and Wildlife Conservation Commission. This is not happening to the extent that we see in St. John and probably never will, but corals are finding their way into the mangroves in Florida. And so folks like the Fish and Wildlife Conservation Commission are launching studies to look for these corals in mangroves around the coastline of the Keys. And this map, my pointer down there, the map at the bottom, you can barely see it, there are little yellow lines, but most of those areas are actually fringed with mangroves. And so there's a lot of territory to look for these kinds of potential ocean acidification refuges. And one of the biggest areas of hope right now, I think, is for protection of these natural refuges. And it really provides a local action that we can take to help against a global problem like ocean acidification. And that's important because often we feel like we can't do anything at the local level to really help with that. But these are the kinds of things we can do at the local level to help combat these kinds of large global scale issues. And I will leave it at that. Thank you.
This particular slide stopped me in my tracks. Fishing is a $9 billion, perhaps much larger industry in the state, commercial and recreational. And I wanted to clarify a couple things about this slide. Kim's absolutely right that we have our shellfish are by far our biggest commercial fisheries, but the South Atlantic Fishery Management Council, for example, manages over 70 species. The state manages dozens of others. The National Marine Fisheries Service highly migratory species manages another 10 or 15 off the top of my head. For the most part, we've done a really good job. I mean, we've pretty much ended overfishing on things, and we've rebuilt most things. I mean, we've done some really brave things to make our own industry sustainable. But when I look at this slide right here, I see the pinnated shrimp and the blue crabs over there. I don't just think of that as food. I think of it as bait. So what terrifies me is that ocean acidification, this invisible threat, we can all see the pollution. We can all see the fish are getting bigger because for the most part, our management plans are working. What we can't see is this dissolution in the ecosystem. So, Kim or anyone, would you all talk about there's so many ways that ocean acidification can and probably is impacting our fisheries and our management strategies. Can each one of you maybe comment on one aspect of that?
Sure. And unfortunately, I think this is probably one of the areas that we know the least about. I mean, we certainly know how the habitat is degrading, and we also know what happens when that habitat disappears. Those fish that can migrate, and those fish that can't usually suffer, and we see reduced populations. And so those are the kinds of things that we're worried about with that. One of our biggest concerns right now is that we just don't know exactly how much it's going to be impacted in Florida. There are regional trends that we see. For example, we've seen that shrimp harvests have remained relatively stable over the last several years, but we've actually seen a little bit of a decline in crab harvest. And we don't know what the cause of that is. It doesn't look like it's a disease issue. And so people are beginning to get concerned because they do see some declines, and we don't have a cause for that. And so, we don't know if ocean acidification is one of the causes for that. And so I would say there's a real call for better understanding. The other regions of the United States have already begun these kinds of studies, particularly our Northwest region. They had a direct impact on their oyster harvesting up there. Their oyster harvest was in drastic decline. They had lost like 40% of their catch. And they thought it was from disease and addressed that problem, and it didn't help. And ultimately, they found it was ocean acidification. And they worked with scientists to actually put together equilibrators on their aquaculture facilities to mitigate the impacts of ocean acidification and bring those harvest catches back up. And so we have seen these impacts in other regions in the United States. We know that Florida is particularly vulnerable, and so these are the emerging concerns and where we need to focus some of our work and understanding.
One thing that Kim and I both talked about is acidification related to eutrophication. So in addition to the climate change, as society releases nutrients into the water, that forms organic matter, and when that decomposes, it can drive the pH locally to a very low level. So this can be episodic. We have algal blooms that form, and then when they collapse, they cause this. This material sinks to the bottom. It's not a place that we're usually thinking about, but it's where a lot of forage organisms for fish live. The pH could, down in that particular environment, even though the water column can recover pretty quickly, could stay low for a month possibly, and impact the forage that'll, through the food web, eventually affect commercially important fish. And another important point about acidification is it may have its strongest effects on the early life history stages of organisms. So when a lot of these organisms, their life cycle revolves forming larvae that swim around the water. These are single-celled or multi-celled organisms that don't have the defense mechanisms to compensate for pH changes. An adult fish, just like a human, can withstand a huge change in pH because they have the ability to regulate the pH balance in their blood. But the single-celled organisms, the eggs and the sperm and the embryos that are formed at that life stage, they don't. So they're much more sensitive to these things. So when we do these studies, it's not just enough to study the adults. You got to think about the whole life history of the organism. Maybe that's where the effects are going to happen.
Ryan, do you have anything to say about this chemical weapon against our fisheries?
Yeah, so the carbonate chemistry is really very simple, but the pH has a lot of effects on other things, as well as nutrients and trace metals. So changing the pH can also change the toxicity of lead, or can make copper more toxic. But it can make nutrients like iron more available and be useful. So it's a very complex chemistry beyond just the carbonate chemistry.
Does anyone in the audience have any questions? Holly?
Thank you. And Dr. Yates, you mentioned something about seagrass and that there's actually a positive in this very, very negative subject. We are anticipating a seagrass die-off, which is obviously going to affect many industries and especially the fisheries. What can we do to maybe mitigate that? Or knowing that's coming down the pipe, what can we do? Do you have any thoughts?
That's a good question and a tough question. It's been very difficult historically to prevent seagrass die-offs. It's hard to predict when they're coming, and when they come, there's not a whole lot you can do to stop them when they start. I think one of the best strategies are some of the strategies that have been proven throughout our state. So for example, in Sarasota Bay and Tampa Bay, they work to reduce stressors to seagrass. And both of those particular locations, as I mentioned before, have put nitrogen management strategies in place that have been hugely successful with respect to seagrass recovery. And so those things are particularly important. Reducing local stressors so that organisms have less stress on them will also help them to be able to tolerate some of the stresses that we can't control. But with respect to seagrass, nitrogen management strategies, programs to reduce physical damage to seagrasses, seagrass planting and recovery efforts. I know, especially in Tampa Bay, they've actually done a lot of seagrass planting to help with recovery. So there's a lot of local actions that we can take to try to help our seagrasses, and also to restore seagrasses after we've had die-offs like that. I think one of the big issues with respect to a seagrass die-off is something that Chris hit on in his presentation, is, once that seagrass dies, then you have a whole bunch of organic matter that begins to degrade, and that actually produces carbon dioxide and can drastically, locally decrease the pH. And so we do need to be particularly concerned about massive seagrass die-offs that can also result in the death of a lot of other organisms just by simply locally reducing that pH. And so,
Wonderful,
Yep.
thank you.
Good morning, Kathleen from Mahogany Youth. We take kids fishing. I have a two-part question. What does the Indian Point nuclear plant and some of those releases do to affect it? And also, is the freshwater flow that we're seeing coming from Lake Okeechobee on either coast, is that affecting it also?
I don't know the water chemistry associated with that particular nuclear plant. What I know in general is that many plants do release warm water
Yeah.
because they use it to cool a lot of their systems. And again, I refer back to Tampa Bay because I study a lot in Tampa Bay. We had some warm water issues there with a power plant. And, you know, that is a local stress that can also cause transitions in the kinds of species that can live near those outfalls. And so, you know, there are lots of different things that can occur with that. Warmer water can cause algal blooms. It can force some species of fishes and invertebrates to move because they don't like the warmer water, but also attract some species. Manatees love it. You know, they'll swim in and they get protection there from cold waters in the winter. And so, you know, that's one of those other local impacts and local stressors that really exacerbate things that we can't control, like the global climate change issues locally at this level. And what was the second part of your question? I'm sorry?
The Lake Okeechobee freshwater flows. And to the first question, when you were talking about, Chris, the upper Keys having a higher impact,
Right.
I thought about that being closer to the Biscayne National Park area
Yep.
and the Indian Point, so.
Yeah, I hadn't thought about that connection, but like the outflow from Lake Okeechobee is, you know, brings nutrients into the estuaries on both sides and is a major aggregating factor to the health of the shellfish in both those estuaries.
What we don't know, I just want to add one piece to that, you know, some of these freshwater flows to our coastal waters are quite natural and have been happening for, you know, thousands, if not millions of years. And one of the things that we don't know about very well is adaptability. You know, some organisms who live in those areas that are exposed to fresh water for periods of time may actually be more resilient and may actually be able to better adapt to changes caused by ocean acidification because they've naturally experienced those large changes in ocean pH and seawater pH. And so, you know, that's an emerging field of study that people are working on. It's a very difficult area to understand because adaptability takes time and experiments usually aren't very long. But that is one other potential area of hope and a bright spot is organisms' potential to adapt because of their natural conditions have made them more resilient.
Hi, I'm Alexis with the Ocean Foundation. I have a question about the economics, and I know you guys are natural scientists, but looking at this figure up on the screen, when you look at the vulnerability, and you mentioned the $9 billion industry, when I think of dependence on resources, I think not just of the fishers or maybe the very specific tour operator, but also maybe the system of charter buses that brings people there and the systems of, you know, other services that are tangential. I'm just curious if there's been a deeper study of the potential economic impacts, getting back beyond just the very point of interaction with the species, but to the whole network of industries that depend on it.
To answer that, I don't think there has, and we desperately need exactly that kind of study because there's probably tremendous knock-on effects of these things that, you know, we start with ecological services what the reefs provide for free, and you need to somehow include that in your economic assessment as well, but then there's all the jobs, and it just percolates through the economy. We need to have an evaluation of it so we know what's at risk.
Yeah, a big part of that understanding comes from really understanding what these impacts are going to be as well. And again, you know, that's one of the reasons why we're looking at it from the standpoint of what we call sort of the low-hanging fruit. What's the worst possible case that, you know, from the geological standpoint and structural standpoint occurs, and that's loss of seafloor and erosion. and how that can just simply affect simple things like coastal vulnerability. And the reason why we focus on these kinds of things is because, one of our best weapons in preparedness for this is getting communities prepared. And, doing predictions so the communities can understand, hey, things look like this now, but in 10, 20, 30, 40, 50 years, this is what they might look like, and you need to pay attention and prepare yourselves for it, because if you prepare for it, then you can better deal with it, right? And so that's why we focus on these kinds of things.
My name's Ray Rocher, a local fisherman. In response to your question, I'll just give you a quick story. It's probably an extreme one, maybe a little more than normal spent on charters, but I'm an advisor to the South Atlantic Council in one category, and before one of the meetings, I had two groups from out of town, and just for the heck of it, I polled them on what they spent. And these two groups came to Miami to fish each one day, rented hotels, ate at restaurants, et cetera, and they both spent just about $7,500 between the two groups, and they both came for 2 to 3 days, stayed at a local hotel, et cetera. So it's like I said, it's maybe a little extreme because, of course, local residents who charter a boat don't spend nearly that much, but it can be as much as almost $4,000 for a day of fishing. And in those 2 days, I think we harvested about 40 pounds of fish and released 6 sailfish. So, the impact on the fishery is not that great versus the dollar spent. And then you have to consider that immediately after my trips, I'm paying a fuel truck, I'm paying my crew. You have insurance and dockage and so on prorated throughout the year per trip. So that money gets bigger pretty quickly, just to answer that question. But the question I wanted to ask is I noticed a comment about, or one point about, types of coral that may be more resistant. I'd really like to know more about that. And one of the thoughts I had just off the top of my head is there are a lot of areas that I'm one of about 150 licensed commercial lobster divers in the state, so I spend quite a bit of time underwater. And there's a lot of areas that are really just mud or sand and don't have much productivity in terms of marine life, in terms of visible marine life. I'm sure there's a lot of small things there, but when you come across areas where maybe a barge lost some limestone or bridge rubble, like Ernie down in the Keys can tell you a lot about the marine life around some of the intentional artificial reefs. Limestone's such a great habitat to grow coral on. Can you tell us more about the types of coral and what research has been done on those types of marine life? And I'm a big fan of artificial reefs and trying to enhance, as a diver, how in murky water when you're getting near any artificial reef is the myriads of small fish swimming towards it for protection. You're in murky water, you can't see it, and when you get to the fish, you follow them, and there it is. So I think that might have some great potential down the road.
Do y'all want to answer the question, though, about which corals have shown the most resiliency?
Yeah, there's a tremendous variability, and I did a study a few years back in Florida Bay, because that's an environment that sees much more extremes in temperature and pH, and found there's really only 2 species of corals that can survive in that environment, and that's Siderastria radians, which is just a small solitary coral that never gets much bigger than this.
We call it golf ball coral.
Thank you. And Solanastria burnoni. Do you have a?
Siderastria is...
No, Solanastria.
Solanastria? Can't remember.
Yeah, I'm not sure it has a common name. But those are 2 very, very tough species that will probably, if you think about a succession, might be the first to invade an area and get established and then create habitat that in turn creates an environment that other things. We're doing some cool research that corals actually, as they build a mound, actually affect the circulation of the water. It can actually cool it measurably, maybe even as much as a degree, so reduce the effect of global warming, just the structure they create.
Anyone else?
Yeah, hi, Eric from Divers Paradise of Key Biscayne. I do a lot of work with We're just on the other side of Bearcut Bridge.
Yeah, sure.
Hi, Chris, how are you? Just to kind of piggyback off of what Ray said, I'm sure we'll meet a little later. I spent a lot of time in the water diving, and working with Durham, there's a big artificial reef program that we do a lot of diving on. It has made a big impact on the diving here. But I wanted to ask you, Chris, about specifically the staghorn and the elkhorn and the mid-'80s disease that really impacted and probably weakened that specific stony structure. I guess kind of from a nested standpoint, if you think about these high nitrate dumps of water, warming, and then maybe potential loss of seagrass that might push the pH back up. Is it a local event to see the I mean, how much of the disease impacted the ability of the staghorn and the elkhorn to resist this acidic event and the die-off? I mean, I guess that's one of my questions.
It's tough because the disease came in the 80s, or very early 80s, 78 and stuff, way before we were, acidification's really become a problem. So there was some thought that the pathogen that causes disease is present in, the human gut and could have gotten into the water through the sewage treatment plants. So there is a possible pollution connection to this disease. But it was absolutely Caribbean-wide, except for the south shore of Cuba, curiously. So it was a very broad-spread event and then just sort of propagated throughout the region.
There's not much as far as how much there was after the disease prior to OA affecting the stony coral, as far as data.
So the connection was that, no, the corals died very quickly within a few years. My point was, that picture I showed you at Carysfort in 2005, the dead coral was still there 30 years later. But now, another 10 years later, it's very quickly starting to disappear. So bleaching kills corals, but the skeletons, that doesn't dissolve them. They'll stay out there and provide habitat for fish for, in that case, another 30 years. So we're thinking acidification is destroying the physical structure, dissolving it and eroding it.
I'd just like to add to that, there are some really interesting results coming out now. There have been some people working on mesocosm studies looking at the effects of ocean acidification on coral disease. And one of the interesting things that they're seeing is that decreases in pH are actually preventing occurrence of black band disease and some of the other diseases. And so there are some interesting twists where, ocean acidification causes a lot of problems, but it may, in fact, help reduce some coral diseases. And so it's one of those other potential bright spots, right? Yeah. If the dissolution doesn't get them first, right?
Reef going up and down, was it live coral or just a dead calcium substrate with algae growing on top of it? How did you measure what was increasing or decreasing?
I think you're talking about Kim's.
Well, I think yours with the North Keys,
So I'm measuring that changes in the chemistry in the water.
The chemistry in
So
the
as
water,
something
not the
dissolves, it releases calcium into the water.
Okay.
And I sensed that was increasing above.
So you weren't measuring the depth
No.
of the coral, sorry.
No, so I like to describe what I did as a leading indicator. It's a very sensitive chemical assay telling us what's going on. It will take years at that dissolution rate to physically go in and observe changes in elevation. But what's tricky is that this dissolution is happening inside the corals where you're not looking at, and it's creating crevices and cavities. So if you break these colonies over, they're like Swiss cheese. So the outside, the living part can look healthy, but if you turn it over, it's just like turning over a dead log in a forest, and all this life scurries out, these beetles and stuff that have been busily hollowing out the coral from the inside that you don't see. The next strong storm that comes through, a hurricane, these things just topple over and fall apart.
And this is one of the reasons why we are actually physically measuring those changes over longer periods of time. Because, Chris measures how much calcium carbonate is produced or dissolved chemically. And as he said, it's very hard to measure that physically because it's a small change. And so we're actually going in and measuring the physical change in the seafloor, the decrease in seafloor elevation and resulting increase in water depth. And by doing that, and that's due to all of the processes, but by doing that, we can start to tease out how much of that change is caused by things like ocean acidification from the types of measurements that Chris does. So by combining those kinds of studies, we can really tease out, well, we've lost this much seafloor elevation, how much of it is due to ocean acidification? So those are the things that we're working on.
What's the technology that you use to do that?
I'm sorry?
The question was, what is the technology that that you use to do that?
Actually, it's really interesting. Back in the late 1800s up through the probably 30s or 40s, they were using hydrographic sounding methods, simple things like lead lining and poling. And they were incredibly, incredibly good at that. It was the National Coast and Geodetic Survey. And so we actually had decades of people going out in everything from rowboats to motorboats and physically taking lead line measurements and triangulating those points in very accurately. And there's a wonderful database of historical, what we call bathymetric, or water depth measurements that exist for the entire Florida Keys. This is actually kind of an interesting story. One of the things that spurred this study is we found that some of the navigation charts actually still include some of that data, and that we were seeing some of these changes in seafloor elevation that hadn't actually been recorded. And so we can take that kind of data and then compare that to modern bathymetric or water depth data that we collect from very technological methods. In fact, we use an instrument called LIDAR. It's a light detection and ranging instrument, and it's actually flown in an aircraft. And it shoots basically a laser down on the seafloor and then returns that signature. And we get very, very, very accurate measurements at very high resolution, millions of points per square meter of bathymetry or water depth measurements. And so we go through a series of techniques to match those data sets up from the historic to the present. And that actually gives us a very simple plus or minus game. Either the water depth increased, the seafloor elevation decreased, or it increased. And so that's it sounds simple. It's a lot of calculations and algorithms and those kinds of things to do these kinds of analyses, but what it boils down to is very simple plus or minus. The seafloor is either increased or decreased. And so by doing that in high resolution, which we're able to do, we can look at where corals once were, and what the change in seafloor elevation has been, because we see pictures like Chris showed earlier. And in some cases, that can be quite a large change in seafloor elevation. And then we can also look at how that affects the adjacent habitats that do not have corals growing on them, because, don't forget, those corals create a lot of sediment. When those skeletons die, they break down into sand, and that sand creates much of the rest of the other seafloor, and it also produces any of the beaches that we have. And so, when we lose those kinds of corals, and you see the kinds of pictures that Chris showed, that also affects the surrounding seafloor. And so those are the ways that we are using to actually get at this at a regional scale, so we can start teasing out the details within the region and within the processes causing it.
So we have time for one last question, and I'm going to hog that time. What I've heard from you all today is that we need to reduce as many other stressors as we can to give these corals and other calcareous organisms a shot and give our fisheries, since they're dependent on them, a shot. But I'd like for you each to close with your opinion on what is the one scientific question that we most urgently need to investigate related to ocean acidification. Start with you, Kim.
So I'm going to cheat, and I'm going to give you two.
Okay.
I'm particularly interested in the vulnerability studies because, in my mind, one of the best ways that we can prepare is to know what's going to happen. And that's one of the ways that we can keep our coastal societies, moving forward. And we're adaptable. If we know change is coming, we can adapt and we can make it work. And the second piece of that for me, and it's the completely 180 contrast, is looking at these natural refuges. There are places that are naturally resilient. And, identifying these locations, understanding why they're more resilient, and using that information to find other locations is really important because it provides that local action that we can take. And it really makes us not feel helpless in doing so. And so it's sort of the two extremes for me. And, what's the worst case scenario? What should we prepare for? But where are the bright spots and how can we use those to help us prepare? So for me, it's that.
I'm interested in the resiliency of corals and how that varies from species to species and even within individuals. You can go out after a bleaching event and you'll see the very colonies of the very same species side by side, and one's completely bleached and another one's still a beautiful golden brown. And I've observed the same thing in my laboratory setups where I stress the corals to pH and find that some of them show 90% of them show an immediate stress response, but 10% are completely immune to it. And those are individuals that are out on the, and I collect these on the reef, so these are individuals that are out there now. So some small percentage of the coral populations out there already have mutations that make them tolerant to these future conditions. So the science that interests me is figuring out physiologically how have they solved this puzzle, and then what can we do to increase the amount of those corals on the reefs.
Mine's very similar to theirs. We know very broadly what's going on, and generally, ocean-wide and even coastally what's happening, but we don't know a lot of the local variability, why some reefs do better, what's the different chemistry of the various reefs, even if they're very close locally. So that we really need to understand that a lot better, and that'll inform us on how we can take better action to preserve those.
Thank you all very much for everything you do.